Welcome to video 3 of lecture 1. This is the final video of this lecture where we're dealing with the normal approximation for discrete distributions. This is in mathematical statistics, and I'm Mark Ledbetter. So we've covered the continuity correction. We've covered all the examples for the binomial distribution. Now we're going to show you how similar this is for another distribution, the Poisson distribution. Okay. So we're doing a Poisson approximation. So if y is a Poisson distributed random variable with parameter lambda, remember that the mean and the variance are both equal to lambda. So what we're going to do is we're going to do a transformation, y minus mu of y over sigma of y. That is our standardized random variable. It's going to have a mean of 0 and a variance of 1. So now we take probability that y is equal to k, and we're going to use our continuity correction. So this is equal to the probability that y is between k minus 0.5 and k plus 0.5. And then we're going to do our transformation. Let me write it out up here. This is going to be y minus lambda over sigma, which is square root of lambda. And then we're going to apply our continuity correction to this. So for k, it's going to be k minus 1/2 here, and then k plus 1/2 here. And so we're subtracting the mean, dividing by the standard deviation. And so then, remember, this is equal. But then we're going to approximate it when we change this to a z, which is has an actual standard normal distribution. W is only approximately has a standard normal distribution. Okay? So that's why we have this. It's very important. It's an estimate. Okay. So recall this. If y is a Poisson of lambda, and then xi is a Poisson of 1, right? Then the sum of these Poisson random variables, if there's lambda of them, that y is the sum of these, then the sum of those random variables is the Poisson of lambda. So in other words, y equals the sum of xi, let's say n, I equals 1 to n, has a Poisson n with parameter n, or lambda equals to n, if xi are Poisson 1 random variables. Okay? Okay. So W is approximately a standard normal distribution. Y can be approximated by a normal distribution with mean lambda and variance lambda. Remember, because the mean and variance are both lambda for the Poisson distribution. Okay, let's do an example. So we're going to let y equal, have a Poisson with lambda equal to 20. We want to find the probability that y is equal to 10. Okay? So to do this, remember that mu is equal to lambda, which is equal to 20. And sigma squared is equal to lambda, which is equal to 20. Okay? So then for A, the probability that y is equal to 10 is going to be the probability that, that y is between 10 minus 1/2 and 10 plus 1/2. So the continuity correction works just the same. And this is equal to, we'll take 9.5, because this is 9.5, and this is 10.5. So I'm going to go ahead and simplify those. So 9.5 minus lambda, which is 20, divided by the square root of lambda, which is 20. And then 10.5 minus the mean, divided by the standard deviation. And this is equal to the probability that W is between negative 2.35 and negative 2.12, And we can approximate that with the standard normal. So we change the W to a Z, which is equal to phi of negative 2.12 minus phi of negative 2.35. Let's go to our table and find these. So it's a negative, so we'll go to the second table, and we need, the largest one is 2.12, and so 2.01, or I'm sorry, 2.12, not 2.22. Okay, so we need 2.1012, 0170. And then we need negative 2.35. So 0, 1, 2, 3, 4, 5, 0.0094. So those are the two values we're going to subtract. Oops. And so this is going to equal 0.0170 minus 0.0094 equals 0.0076. That is our value. And I believe, so I haven't calculated the actual value here, but this should be a pretty good approximation, okay? Because n is 20 here, and so we'll have we should have a pretty good end. Y is 10, so we should have a pretty good approximation here. Okay. B, the probability that y is less than 10 is equal to the probability that w is y is less than, I'm sorry, let's not take that step yet, that y is less than 9.5. Why? Because again, I need, here's 10, I want less than 10, I cannot include 10, so I'm going to come over to this side, which is 9.5. If I do 10.5, it will include 10, and I can't include 10. Remember, discrete, I have to be very careful with this. And so this is equal to the probability that w is less than 9.5 minus 10 over square root, minus 20 over the square root of 20. So minus lambda over the square root of lambda, which is equal to the probability, which is not equal to, which is, yeah, it is. Well, we won't change variables yet. W is less than negative 2.12. Now, approximately, this is the same as Z is less than negative 2.12. And if we look up the negative 2.12, which we did last time, that's 0.0170 here. So this is 0.0170, and that is our answer. And then C, we want the probability that y is greater than or equal to 15. And so I have 15. I want to include 15, so I need to go below it, so that's 14.5. So this is going to be the probability that y is greater than 14.5, which is equal to the probability that w is greater than 14.5 minus lambda over the square root of lambda, the standard deviation, which is, still equal, which is equal to the probability that w is greater than 1.23. And now this is approximately equal to the probability that z is greater than 1.23. And this is equal to 1 minus the probability that z is less than or equal to 1.23, which is 1 minus phi of 1.23, which is 1 minus, now let's look up 1.23 in our table here, our first table. So 1.2, and then 3 is going to be right here, 0.8907. Now I could look up 1.23 in the other table to get this directly. 0.1093. Oh, wait, yeah. So, Yep, so I want greater than 1.23, right? And so greater than 1.23 is in this table, so we're going to get a 0.1093, or we could say 1 minus 0.8907. So 0.093, 10.1093. Okay. So to do this, to get these, I didn't do the approximations. I could do it for y equals 10. Let's look at the probability that y is equal to 10, and that is equal to, let's see, the Poisson distribution is e to the negative lambda, lambda to the x, or y in this case, over y factorial. So this is going to be e to the negative 10, 10, e to the negative 20, because lambda is 20. So e to the negative 20. And then I've got lambda, which is 20. Oops. Raised to the 10 over 10 factorial. Let's see what my calculator gives me for this. Second, e negative 20 times 20 raised to the 10 divided by 10 math. Oh, no. Factorial 0.0058. So I got 0.0058, and my answer to the first one was 0.00676. The actual the estimate 0.0076 minus 0.0058 over 0.0058. 0.0076 minus 0.0058. No, 0.0076 minus 0.0058. I did a multiplication that gave me a weird number. 0.0018 over 0.0058 is a 31.0% error, so not very good. So we'd need to increase n from here, remember that each xi, so n is going to be equal to 20 in this case, because each xi is a Poisson 1, okay, random variable. So we'd certainly need a sample size of larger than 20 in this case to get a better estimate. All right, so that's how we do it. And so please make sure you update your formula sheet if necessary. If you have any questions, come to virtual office hours. If you need help before or after that, and after that's possible, then by all means email me. I'll help you as soon as I can. And please take care of yourself, and we'll see you next time.